Yeah, camps on everyone. Let's start off. The last thing we have started with the friction. Let's go ahead with a few more problems. Let's say we have an incline, 45 degrees, 45 degrees. This is 2m. This is m. And the friction mu is equal to 1 by 3. Find the acceleration of the blocks. Are the cams on? Straightforward, easy one. Let's give it a try. Find the acceleration of the blocks. How do we do this? So first thing, right, in this kind of questions, you need to check whether the system can even move in the first place. That's the headache with the friction. Remember, friction ka job was not to give the maximum value. So if you look at the scenario here, what is the pulling force here? This will be 2 mg sine 45. So what is this force here? This will be mg sine 45. And if you try to look at the friction, so this friction will be opposite here. Let it be F1, and this friction will be in this way F2. So if you try to calculate F1 max plus F2 max, so understand this, until and unless you generate at least this much friction, you're not going to move. So F1 plus F2 max will be how much? This guy will be mg sine 45. This will be your normal reaction, and this will be your mg cos 45. This will be a normal reaction, and this will be 2mg cos 45. So this would be mu is 1 by 3, 1 by 3, 3mg sine 40 cos 45. That is our total friction. Mu into N1 and mu into N2. So this comes out to be mg cos 45. So this is the maximum friction. And what about this net pulling force there? If you see, the net pulling force is also mg sine 45. That means the friction exactly balance the amount of friction there. So both are equal. The system will not move. Acceleration is 0. Is that making sense, everyone? Suppose if you take mu ka value more, let's say if mu is equal to half. So let me make it more actually. If you make it mu is equal to half, then it will be even more bad. So then this will be 1 by 2, and this will be now 3 by 2 mg cos 45. And then we will argue like this thing. Since net force is less than F maximum, the system won't move only. You don't have enough force to break the friction. Therefore, the system is at rest. Clear with this? So this is one thing. You have to check whether the system is even moving in the first place. So there is no acceleration here. Nothing moves here. Won't F1 be in the opposite direction? Yeah, I'm sorry. Should be in the opposite direction. Yeah. Clear with this? So that's one thing. You directly always cannot write the equation. You have to check for the value of friction. Let's see one more. 45 degrees. Mu is equal to half. We got a block here, which is 10 root 2 kgs. This is connected here to a block of mass m. Find the value of m if the system is at rest. This is a good question, right? You will see variations of this later on in other chapters. So you have one block on an incline and one block on the other side hanging. Find the value of small m if the system is at rest. What do you think? Any answers? No, the 30, 40 seconds niche look. That's not the only answer. How many answers are there? There are infinite answers. That's what I'm saying. See, you should know the nature of friction. Friction ka job is not to apply maximum. So let's calculate and check it out. First of all, what is your F maximum here? If you look at the forces here, so this guy is pulling down, which will be mg sine 45, which will be 100. This will be tension, this will be tension, and this will be small mg. N ka value is mg cos 45. That is also 100. And what is the maximum friction? F max will be 50. Now look at the two cases here. Let's say you kept the block ka weight very high. Matlab you kept a very heavy block. Maximum small m. Now, if you keep the weight a lot, what do you think will happen? The block will try to slide up, isn't it? If you keep a lot of weight, the block will try to slide up. If the block is trying to slide up, then what will be the FBD? We have tension, we have mg sine 4500, and we have F max will be downward. That means we get tension is equal to 150 and tension is equal to small mg. We get m is equal to 15 kgs. Meaning for a weight of 15 kgs, anything more than 15 kgs, you will go up. But there is another possibility. What if you keep the weight very small, minimum m, meaning you don't have enough mass to stop the block from slipping? Now what will happen? The block will try to slide down. So this is what I was saying. See, friction ka job is not to oppose you. Friction will see, are you going up or are you coming down? So friction will see, oh, this guy is trying to go down and I'm not happy with it. So now this will try to oppose this guy. Now the tension will be up and the friction also will be up. And this is 100. So now we get tension is 50. This is equal to mg. We get m is equal to 5 kg. That means the minimum weight, if you keep anything less than 5, you will slide downward. If you keep anything more than 15, you'll slide upward. Means for any value between 5 to 15, you're safe. That is because friction can change its magnitude and friction can change its direction also. Is that making sense? So if I show you with some numbers, look at this thing. Try to answer this, you will get the thing for this. How friction behaves. Friction will not give maximum every time. This is clear, mg sine 45, this is 100. Okay, now listen this. Let's say if your tension T is there, if tension is also equal to 100, what is the friction? Do you need friction to stop the block from slipping? No, right? So if T is 100, then friction is 0. Suppose if T is 120, then what do you think will happen? If tension is 120, mg sine 45 is 100, that means you're pulling up with 120. Friction will say, oh, I'll come and give 20 newtons. You're getting the catch? Friction ka job is not to give 50. Friction will give only how much ever is required. What if I give 140? Then friction will say, oh, I'll give you 40. What if you say tension is 80? Now friction will say, oh, you're giving less than 80. So friction will come up now and friction will give 20 upward. Is that making sense? So friction ka value can fluctuate minus 50 to plus 50 on both the sides. That means you get a range there. You can have 100 plus 50 or 100 minus 50. I hope this is making sense. So, and if you keep doing this at F maximum at 150, you will get friction as 50 max. So friction ka value will depend on what is the value of small m. If you keep small m too heavy, then the block will try to go up and friction will be down. You keep it too light, then it will come down. So is that clear, everyone? Easy? Making sense? It's a pretty good question. So yeah. So you get a range of answers. It's not a single answer there. Let's see the next one. Let's get this. Right. The Ahana got the answer. Yeah, Thanmay also got an answer. Rohit also got it. Yeah, most of you did get it. So we have two hemispheres of radius capital R and small r, and we have a rod which is lying at rest. Find the minimum ratio of r by r for which the rod will not slide. Yeah, get it. Step one, draw the free body diagram. That's how you always start. So remember, this rod will make a tangent. So what are the forces? This would be N1. This would be N2 passing through the center, should be normal. This will be friction F2 and this will be friction F1, and this rod is pulling with mg sine theta. So we can extend this. This will be theta. So we don't know what is theta. Mg sine theta, and this is mg cos theta. So we can, since we want the minimum radius, f has to be mixed maximums. It is on the verge of slipping. And the frictions are just become maximum. So therefore, F1 and F2 are max. F1 max plus F2 max must be equal to mg sine theta. But F1 max plus F2 max will be mu into N1 plus N2. Now, I don't know what is N1, I don't know what is N2, but I know what is N1 plus N2. N1 plus N2 will be mg cos theta. We got tan theta is equal to mu. Later on, we will learn this. This is called angle of repose. Great. Now, what is being asked? They're asking the ratio of capital R by small r. How do you get that? At this point, it is just a little geometry there. So if you see, this is 90 degrees. This was theta. So from here to here, if I draw a triangle like this will be theta. This distance will be r minus small r. And this distance will be r plus r. Um, this is r and this is small r. They're parallel lines there. So from here we get sine theta will be r minus small r by r plus r. This is the relation between them. And we know tan theta is equal to mu. So from tan theta, how to get sine theta? This is theta, this is mu, this is 1. This is the hypotenuse, which is mu square plus 1. So sine theta will be opposite side, mu by root over mu square plus 1. Substitute here. Then we can use that component or dividend thing. Then we can do r minus r and cross multiply, whatever. It will be r minus r is equal to root over mu square plus 1 plus mu by root over mu square plus 1 minus mu. So that's your answer. So this is all geometry, and we get tan theta here from the forces, and we get tan theta here from the triangles. Is that clear, everyone? You can simplify it further, but that's your answer. Any doubts on this? Clear? Shlok, Soumya, Ananya? Next one. Next one is again a standard mains and CET level question. Should remember the result. Exam may, if it comes, you just mark it and go ahead. So block M. Find the minimum force required to move the block. Just to tell you, it is not mu mg. Now try. Multiple times it has come. It's a repetitive question. So it does keep popping up in one or the other exam. Remember, you'll be giving a lot of exams. You'll be giving 2 mains, 2 bits, 2 CET, 1 advance. If you're writing UG exam, right? We have Manipal, MAIT, all those exams. You'll be writing almost 9 to 10 bunch of exams. It will pop up some or the other. So you know the answer, you'll mark it and go ahead. So saves you time, nothing much. So standard one. What's the answer? Yeah, right, Yukti. Now, the first common mistake, right? When they say minimum force, no one told you force is horizontal. The force can be at any angle. So let the force be at an angle theta. Okay, how does this help? The catch is this. I can use some of the force to pull the block. I can use some of the force to decrease the normal reaction. By decreasing the normal reaction, you can decrease the frictional force. There are 2 ways to defeat your enemy. Either you become stronger than them or you make them weaker than you. Force does both the things. It will use some part of the force to decrease the friction and some part of the force to drag it down. Now this will be F maximum. Since you're asking for minimum, this is about to slip. This is what I was saying. Unless you're damn sure it is slipping, don't put F max there. Then you're done. So that's the there. N is equal to mg minus F sine theta. So remember, theta is variable, F is also variable. F cos theta is equal to F max. So we get F cos theta is equal to mu n, that will be mu into mg minus F sine theta. We get F is equal to mu mg by cos theta plus mu sine theta. So this is the force for different angles. If you apply a different theta, we get different force. So to get maximum force, we need to minimize this, then minimize the denominator to maximize the force F. And we know from trigonometry, a function a sine theta plus b cos theta is always less than equal to root over a square plus b square. So if you do that, we get f max will be mu mg. A का place में 1 and B का place में mu. So 1 plus mu square. This is the minimum force, which is definitely less than mu mg. So mu sine theta plus cos theta must be less than equal to root over mu square plus 1. Standard result. Mu mg by root over 1 plus mu square. So this is the reason, right? If you see, right, pulling and pushing, there's a technique like that. Pulling is easier than pushing, because when you push, a part of the force will increase the normal reaction, friction becomes more. When you pull, a part of the force will decrease the normal reaction, so force will decrease. So there. All clear with this? Easy one, standard question though. Let's see one more. We have a weird incline. On this incline, we have a uniform rope. This is a uniform rope on the verge of slipping. Meaning a little disturbance and this whole thing will slide. So this is a rough incline, so the surface is rough. The height is h and the base length is L. Find mu. Nothing is given. Mass of the rope, length of the rope. It's a uniform rope, इतना तो पता है. Yeah, that is the maximum value, right? So when you keep maximum value in the denominator, sorry, you want to find minimum force, right? I did a mistake. So you want minimum force, sorry. This is the minimum, this you should maximize. Yeah, my mistake, I wrote it wrong. Minimum force, you're right, Rohit. Let's get this thing. You guys remember we did something like this thing in NLM? So if you see a question like this and you have no idea what the hell to do, how do you solve the question? See, understand one thing. Knowing how to solve a question and getting an answer are two different things. You can get an answer in the exam even without understanding actually how to solve the question. So if this question comes in the exam and if you have no clue what to do, you know what I will think? The question, right, always gives you certain things. Understand one thing. First of all, did you tell me what is the shape of this random curve? You didn't tell me. That means you're indirectly telling me no matter whatever shape I take, the answer should be same. Isn't that what you're telling me? Second thing, you didn't give mass of the rope. So you're saying it doesn't depend on mass. Fair enough. So the first thing is the main thing. You're telling me indirectly, you take any shape, the answer will remain same. So then what I will do, I don't know how to do for this. So I will take a incline. Answer should be same, right? I will take an incline. I'll put a rope. Then I will say this is mg sine theta. This I'll say mu mg cos theta. I will get tan theta is equal to mu. And tan theta is nothing but h by L. That should be the answer for this question. I got the answer. I still don't know how to do the question. But I got the answer for the sake of the exam. Now, if this is an exam, move on. Go to the next question. Forget about this thing, done for the day. But you're learning now how to do this. Because then what will happen? Some guy will come and do mu is equal to mu naught x, and then you will die. They will change the friction, which is changing with x coordinate. So yeah, you should know how to do for that sake. So people have this misconception, your subject is good, so you will score well in the exam. Not necessary. Yeah, your subject is bad, you won't definitely score, but your subject is good doesn't mean you're going to score. So how do we do this thing? Yeah, H by L is the answer. We know the answer. So listen to this. So whenever we have something weird like this, we always start with a small slice. So take a small slice somewhere here, ds. Let's draw the FBD of the small slice. We can treat it like a small incline here. This theta is variable. Theta is changing every instant. Now, if you look at the forces on this, we have dmg sine theta. That is a weight which is trying to pull you down. And this friction will be df max. That is the friction which is trying to stop you. This is your dmg cos theta, which is your normal reaction, dn. So all these are small forces on this. Now, can I say all the frictional forces acting on this rope must be equal to all mg sine theta is acting down? The mg sine theta is trying to drag you down and the frictions are trying to stop you. So total frictional force. Actually, if I draw the full FBD, there is two more forces. We also have tension T plus dt, and we also have tension T. We don't need it right now, but there are tensions on the rope. That small segment, we have tensions. We will see them later on. So, and dm is the mass of that small rope. dm is the mass of that small piece. Which I can calculate. So let's see. So the total friction. So all these frictional forces must be balancing the total component of weight along the string. Net pulling force thing. Total component of weight along the rope. I don't know the length of the rope. Let it be small l. Let the length of the rope. I already used capital L. Let the length of the rope be small l. So what will be dm? dm will be total mass of the rope by total length of the rope into ds. Clear with that? Total mass by total length into ds. I don't know capital M, I don't know dl. See what will happen. So integral df max is equal to integral dmg sine theta. What is df max? Mu into dn, which is mu into dmg cos theta is equal to integral dmg sine theta. You should not cancel dmg, they're inside the integral. Let me write in the next page. And this is what I was saying. If they mess up something here, this is the point, where you have to change your integrations. So this will be total mass by total length into ds g cos theta. This will be m by L ds sine theta into g. Now in this piece which you took, this was your ds, this was your theta, this was your dx, and this was your dy. So we can clearly see here ds cos theta is dx, ds sine theta is dy. I don't know theta, I don't know ds, but I don't know what those are. So this will be mu capital M G by L integral ds cos theta. This would be M G by L integral ds sine theta. M by will cancel, G will cancel on the both the sides. This will become integral, this is dx. This will become integral dy. This will go from 0 to h. This will go from 0 to L. Integrate this. Mu into L is equal to h. Mu is equal to h by L. Clear what we did? This is how it is actually derived. And if you see, right, it doesn't depend on the shape of the rope, nothing. Now, that variation which I told you, if they say mu is equal to mu naught x, you know where it will change in the problem? This mu here will be mu naught into x. Then you will get mu inside here, and you'll get x into dx. This will become mu into L square by 2. Can you see the adjustment there? If mu is depending on x, then the left-hand side, you'll get an x into dx ka term, and then you have to integrate. And so that is the reason you should know how to do also. If you don't know how to do, this is what will happen. They'll mess up something and you won't understand how to approach. Please have a look at the steps, what we did again. So I took a small piece. Then I said, on that small piece, there is a small friction and a small dmg sine theta. So on this rope, right, all these dmg sine thetas are pulling the rope down. And all these frictional forces are fighting back. df, 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 and df, and df. So all these frictional forces must be equal to all these mg sine thetas. Integrate them. Then we got the dm is total mass by total L. Remember, I don't know m, I don't know L, but they will cancel out. And ds cos theta become dx and ds sine theta become dy, and you're done. All clear with this? So you can write it in a more generalized way. Let's say we have some weird surface like this. And let's say we have a rope here. Again, uniform rope. I'm not able to draw it properly. So this question, right, will work only when it is on the verge of slipping. Huh? Because see, if you're not on the verge of the slipping, you can't say friction is maximum. Then you can't write mu into dn. Then you can't solve. The rope must be on the verge of slipping. Then the result goes like this. If this is length L, this is height h1, and this is height h2. So the friction mu is given by the difference in height, h1 minus h2 by L. That's it. Meaning you just take this difference and finish it off. You take that corner and this corner, join them. This will be h1 minus h2, and this will be L. Mu is equal to the difference in height between the two corners by the horizontal length between them. This is your answer for any shape. Because if you see the previous result, I derived it for any random shape. So works. All clear with this thing? So let's see how they'll frame a question on this. So B part of the question. We have a hemisphere. Fixed, rough hemisphere. We have a rope like this. This angle is 30, this angle is 60. Friction is mu. The rope is on the verge of slipping. Find mu. I can ask you one more better question on this. Find the point on the string where the tension is maximum. So on this segment, there is one point where the tension is maximum. And I hope you remember this logic. Free ends always have zero tension. So here the tension is zero, here the tension is zero. But there's a tension in the middle. That would be a good question to think of. But let's get this that you can try as a homework. Find the point on the string with maximum tension. Mm, 2 minus root 3, yeah. Let's see. You can directly use the formula which I gave you right now. So this height here will be, this is the radius r. This will be r sine 30. This will be r cos 30. This will be r sine 60. This will be r cos 60. So what is the difference in height? So mu is equal to h1 minus h2. So the difference in height will be r cos 30. That is this height minus this height, right? And you want the horizontal length. So this length here is r sine 30 plus r sine 60. This height is your r cos 30 by r cos 60. Yeah, just dump there in the formula and you're done. R cos 60 minus r this by. You don't need r. R will get cancelled. Simplify this. You will get some root 3 minus 1 by root 3 plus 1. You can simplify further, you'll get an answer. 15 degrees, it seems. Yeah. All clear with this? So that's one thing there. So that is all, based on this thing. So if you know this result, it saves you there. You should know how to do. See one more. We got a long incline. This is theta. This is mu. We have a block here of mass m. Someone kicked it with speed u upward. The block goes up and down. And comes back. Find the ratio of time of ascent by time of descent. Assume the block never stops. What if? What, Anish? I don't know what you typed. Type your answer properly. Just saying some random number, no one understands. What? You're not typing the answer properly. 15 degrees from where? 15 degrees from here? 15 degrees from where? Here? What? Don't. Let's get this. Nah, that's not the answer. Let's get this, everyone. Try this question, Anish. Let's get this. What is the answer for this? Hmm. Root sine theta. Yeah, you're not going to get a good answer here. So listen. The thing is, while going up and coming down, you have different accelerations. So theta, so when you're going up, the velocity is upward. So your mg sine theta is backward. Friction is also backward. Since you're sliding, F is max. Acceleration will be A1, which is backward. Mg sine theta plus mu mg cos theta is equal to ma1. We get A1 is equal to g sine theta plus mu cos theta. Now what will happen? This will travel, and somewhere it will stop somewhere here. This would be the distance traveled s. So first thing we can get the time. V is equal to u plus 80. V is 0. U is initially u, and this is minus a1 into time t. This is your time of ascent. And what about the distance traveled? V square minus u square is 2as. Final velocity is 0. This is minus u square. This is 2a1s. You will see why you require the distance traveled. S is equal to u square by 2a1. This is the first part of the question. Now the problem is while coming down, your acceleration has changed. Mg sine theta is down, and now your maximum friction is on the other side. So you're going up with a different acceleration, you're coming down with a different acceleration, therefore they won't be equal. So here we get A2 will be g sine theta minus mu g cos theta. And how much are you traveling? You're traveling the same distance. That's the reason you needed that S. See, you won't come back to rest again. When you come back here, you have some speed v dash, which I don't know. This will not be same as the initial speed because you lost energy. And then you can use the equation S is equal to ut plus half at square. What is S? U square by 2a1. What is your initial velocity? 0 because you're starting from rest. This will be plus half a2 time of descent square. This will give you time of descent, which is u square by a1 a2 ka root, which is u by root a1 a2. You are asking for the ratio of time of ascent by time of descent. Ascent is u by a1. This is u by root a1 a2. And this would be root over a2 by a1. Sine theta minus mu cos theta by sine theta plus mu cos theta. Yeah, check your answers. There'll be a root there. Right, Anish? Yeah. All clear with this. Any doubts on this? So be careful with that. So while going and coming back, it's not the same thing. Let's see one more. We have something called angle of repose. This is just a bit of a theory. So when you take a block on an incline, mg sine theta, this is your friction. So if you don't want the block to slide, so remember if the block is not slipping, friction is mg sine theta. That's it. It's not mu mg cos theta. It is not all that. If someone says the block is not slipping, then friction is exactly giving what is required, which is mg sine theta. And then we know the friction must be less than equal to maximum mu into mg cos theta. So from here we get, so mu should be greater than equal to tan theta, or tan theta is less than equal to mu. So this is the condition for no slipping. If your tan theta is less than mu, then blocks won't slip. So this angle is called as the angle of repose. Yeah, basic standard, nothing much. So on steep inclines, you need more friction to stop. Kind of makes sense. If the angle of inclination is less than tan inverse mu by mu, the block will slide. So it's called angle of repose. So the word is important. Now, in this, we have cases, how they will use this angle of repose. So one case is height of a sand cone. If you ever been to a beach, right, and if you try to make a sand cone, you must have noticed it. As the height increases, the base also keeps becoming bigger and bigger. So if you make a cone out of sand, if you look at any sand particle here, there are two forces which are, pushing the thing up and down. So there is a mg sine theta, which is dragging you down. This was theta. And there is your friction F. Same story again, F max. So this is the FBD of a sand particle. This radius is r and this height is h. So we get from here tan theta is equal to mu, angle of repose. So that is the maximum limit you get, and tan theta is also equal to h by r. So there, this is the relation between height of the sand cone and the radius of the cone. Means if you use a very smooth sand, the friction is very less. So to get 1 meter height, if you take 1 meter radius, you get only 10 centimeter height. That's the reason it is very difficult to make the sand castles in the beach because they don't have enough friction. But if you use clay is very sticky. They have very high friction. So when we make murtis, right, the statues or whatever, when we use clay, you can actually go to more height even with a smaller base. So you need good friction to get a more height. So this is one formation of asking height of a sand cone. The second model is this insect walking in a bowl. So if you have a bowl here, again, we are talking about an ant or something, not a special insect. It doesn't have all that, that lizard ka jo hota hai, the sticky stuff. We are assuming a regular thing. Again, same thing happens. When you try to walk here, at some point, like this as theta, the mg sine theta is dragging you down. The reason you're able to walk again is because of friction. F max is trying to push you up. This angle will be again tan theta is equal to mu. So you cannot climb more than this. This is the maximum angle an insect can climb inside a hollow hemisphere. Clear with this? So that's little based on angle of repose. So let's see one small question on this. So let's say we have a rough bowl, which is like f is y is equal to x cubed by 3. And let's say coefficient of friction mu is equal to 1 by 3. This point is your origin. So an insect decides to start walking on this surface. Find the maximum height this insect can climb on this surface. Find the maximum height insect can climb. We have a hemispherical bowl here, and let's say mu is equal to root 3. Someone took some dust and they started sprinkling on top of it. So when you sprinkle the dust, part of the sphere got covered in dust. The whole thing is not covered, only a part of it is covered in dust. So this is the area covered in dust. Find the area. Let's see how will you do this. What is the surface of the bowl is of? Tanmay, I'm not sure what you're asking. The surface of the bowl is rough. Yeah. Let's get this. Remember the story, when you're climbing, the reason you're able to climb is because of the friction. So as you're climbing, at some point, if I just draw a tangent here, I can treat it like an incline. So the frictional force is actually making you walk F max, and your mg sine theta is dragging you down. And this F max is nothing but mu mg cos theta. So when these two forces become equal, that is the maximum you can climb. After that, you're going to slide, basically, which is the angle of repose. We get tan theta is equal to mu is equal to 1 by 3. But we also know from calculus, tan theta is nothing but dy by dx. Slope, right? So dy by dx is 1 by 3, and this guy would be x square. So we get x is equal to 1 by root 3. If x coordinate is 1 by root 3, then y coordinate will be, how much is that? 1 by 3 and 1 by 9 root 3. Clear with this? That's the maximum height you will reach. Is that making sense, everyone? What about the second one? Pi r square by 2. Okay. Not sure though. Yeah. What about the second one? Same story, same. The reason the dust is not falling down is because any dust particle which exceeds the angle of repose will slide. So all the dust particles after this, so this is your angle of repose. Because after this, at this point here, the friction has become maximum. This is F max and this is mg sine theta. After this point, it is becoming so steep, the particles will start sliding down. So we get the angle of repose tan theta is equal to root 3. So we get theta is equal to 60 degrees. Now, if you guys remember the formula, the area is given by 2 pi r square into 1 minus cos 60. This is 2 pi r square, 1 minus half is equal to pi r square. Now, in case you're thinking, oh, where is this? We did this thing in calculus. And I told you this will come. You guys remember this question? Surface area of a hollow sphere, 2 pi r square, 1 minus cos theta. देखा सेम क्वेश्चन दिया था. Dust is sprinkled area covered in dust. This is how they will use this. So page number 126, calculus. In case you forgot, you should refer that. That result is useful. Clear with this? Take a break. Come back by 9:40. We'll continue from here. Yeah, let's go ahead. Let's see one more. Cams on everyone. You got a wall here. You got a floor here. Mu is equal to half. We got a chain here which is hanging. It's like this. This part is L by 3. This is theta. This is fixture. Mass of the chain is M and the length is L. So 1/3 of the chain is on a table, on a rough table. Gravity is present. The chain is on the verge of slipping. Find theta. Let's get this other to keep your cams on. Let's give it a try, everyone. Any answers? Are those cams on? Let's see. So step 1, draw the free body diagram. So we will draw the FBD for two pieces, okay? One is that hanging part. And the horizontal part. Now the chain is on the verge of slipping. So if this is tension T, this must be F max. This weight will be mg by 3 because it is 1/3 of the length, and this will be the normal reaction. So we get tension mu is equal to mu into mg by 3. Mu is F, so this tension is mg by 6. That same tension is acting here. Here we have a different tension, let's call it T dash. And this angle is theta. And this rope ka weight is 2 mg by 3 because that is 2/3 of the length. And we can clearly see the vertical component here, T dash cos theta, will be 2 mg by 3. T dash sine theta will be the horizontal tension T. So if you divide this, I get tan theta is equal to T by 2 mg by 3. But T is mg by 6. mg will cancel, we end up with 1 by 4. Check. Clear with this? All we did was just drew a free body diagram, nothing much. All clear? Draw a free body diagram. So the word right on the verge of slipping, that tells you the F is maximum. That's the main thing there. Let's see one more. This is another good one. We have a conveyor belt. What is a conveyor belt? In an airport, if you ever been on a travelator, the horizontal thing, that's like a conveyor belt basically. It's just dragging. So it's rotating this way, it is rotating this way. The friction is 0.2. The length of the conveyor belt is L. And the conveyor belt is going with a speed of 10 meters per second. Now what you did, you took a block M and you gently placed it on top of the conveyor belt. Initial velocity is 0. So once you drop this block here, this will start sliding and it gets thrown away from here. It goes and falls on the floor. From here to here, this height is 80 centimeters. This distance is your range. L is the length of the conveyor belt, which is not given. A block of mass M is gently placed on a conveyor belt moving with a speed of 10 meters per second. You just dropped on top of it. The block slides on this and leaves the belt and falls on the ground. Right? Plot the range versus L. How does the range change with the length of this belt? Means what if I take a 1 meter belt? What if I take a 10 meter belt? What if I take a 100 meter belt? But the belt speed is 10 meters per second. That you cannot change. Let's give it a try. Let's see how will you do this thing. Hope the picture was clear. Actually, this is a technique, right? They used to separate, a tin ore from the iron ore. So what they do, they have this conveyor belt. They make this thing magnetic. So whenever they are mining tin ore, it also has some contamination of iron pieces. So the tin and the iron pieces, when they're moving, the iron pieces get attracted. So they slow down and they fall here. The tin pieces don't get attracted, they fly farther. So you get two heaps. So this is a mechanical separation of tin and iron ore. So you can do all that stuff. Figure out, na, Yukti. See, the speed of the conveyor belt is 10. I never said block speed was 10. If you put the block on the conveyor belt, what is the direction of friction? Ask yourself. The floor is going forward, the block is not moving. So what will friction do? Friction will support the block, isn't it? When you put your leg on an escalator or a conveyor belt, the friction is actually forward. Try. Take a minute or two. It's a good one. There is just a small trap. Like think. Take a minute or two, then I'll show you. So if I just see the free body diagram, so when you take the block M, you're gently placing it. So there is a relative velocity. There'll be friction on the block maximum because you're slipping. There'll be friction backward on the conveyor belt. So technically conveyor belt should slow down. That is the reason we have this motors which will maintain the speed. That's why you need to provide electricity for the conveyor belt. Anyways, so this F max will be mu mg and this will give you an acceleration. So F max is equal to mu mg is equal to ma. So you don't need the mass. So A is equal to mu g. Mu is given as 0.2. So acceleration is 2 meters per second square. So that is the best thing. That means you drop a coin or you drop an elephant, they accelerate the 2 meters per second square. Then what? So that means on the conveyor belt, now understand, when you put it on a conveyor belt, you won't get the speed 10 immediately. The reason in real life you think you get the same speed is because the conveyor belt is going so slow and the friction is so high, it will barely take, few seconds to get that speed. Didn't you ever felt this? When you put your leg on the escalator, don't you feel that jerk suddenly? That's the reason if you see na, kids and old people get scared to get onto the conveyor belt. Because the moment you put your leg for a moment, there isn't kind of an acceleration. There's a small slipping. We do that. So if you look at this block here, this thing has an initial speed u0. Now it has an acceleration a is equal to 2. By the time when it reaches this corner, it will gain some speed v and this length is L. Since a is constant, I'll use the kinematics equation. V square minus u square is equal to 2as. So I get v is equal to root over 4L. This is the speed. So the speed of the block depends on the length of the conveyor belt. If the length of the conveyor belt is too small, even before the slipping stops, the block will leave the ground. Is this making sense? But there's a catch. What happens the moment the block reaches 10 meters per second? So as this is slipping, the speed is increasing. At some point, the block will reach 10 meters per second. The moment the block reaches 10 meters per second, the slipping stops. They both have same velocity. If the slipping stops, then the friction will say, my job is done. I made sure both of you are going together. Therefore, F becomes 0. So the friction will suddenly stop acting. If the friction suddenly stops acting, then acceleration is 0 and the body continues with a constant velocity. So that is a catch with a conveyor belt. Your speed cannot exceed 10. That's the whole thing there. So block moves with constant speed 10. If you reach 10 meters per second, if your speed is only 8 and by then the conveyor belt is over, then you'll fly out with 8. So how much is that length? So V is equal to 2 root L, right? Must be less than equal to or equal to put 10. So we get L is equal to 25 meters. So there, that is a limitation. If your conveyor belt length is less than 25 meters, the block will never stop slipping. It will always keep sliding, and then it will fly off. But if length of the conveyor belt exceeds 25 meters, the speed becomes 10 and then you remain constant. Is this making sense, everyone? So up to a certain value, it does depend on the conveyor belt length. So this is how you write the velocity formula. So velocity of the block is 2 into root L. If the length is less than 25 meters, the speed is 10 meters per second. If the length is greater than equal to 25 meters. And then now the question has become a projectile motion. You're throwing with V. The height of the building is 0.8. Time of flight will be root over 2h by g. That comes out to be 0.4 seconds. That's your time of flight. So your range also will depend on the answer again. So what is range? Range is equal to horizontal velocity into time of flight. So the range will be 0.8 into root L. If length of the conveyor belt is less than 25 meters, or it is 4 meters if the length of the conveyor belt is greater than 25 meters. So if you try to plot this, R is equal to 0.8 root L. This is R square is equal to 0.64 L. This guy is looking like y square is equal to ax, a horizontal parabola. So if you plot a graph between R and L, this is a horizontal parabola, and then it becomes a constant. This occurs when L is 25 meters, and when the range is 4 meters. That's how the graph looks. Is this making sense, everyone? So you need actually enough escalator, that entire rough surface in order to stop slipping. The thing is, you won't get the speed immediately. It takes time. The friction between them is accelerating it. So the regular escalator or the travelator we use in the airports, they have very high friction and they have very less speed. So you will get the speed within maybe a fraction of a second. So you really don't notice it much. 10 meter per second is pretty fast. Clear with this? 10 meter per second is 36 kilometers per hour. You don't travel that fast on an escalator. People will start flying out. Any doubts on this? This is a good one. Not too tough, little different. Most people don't realize that once you reach 10, friction will stop acting. That's what I was saying. Friction, right, doesn't care about anything. It'll just say only one thing. Am I slipping or not? The next one, let's see. This is even better. This is the top view. You're seeing from a drone or something. We have a conveyor belt. This is a top view. The belt is moving with a constant speed of 3 meters per second. This is a rough conveyor belt. The width of the conveyor belt is W. We don't know this width. Best example, think of your treadmill. This is how the treadmill surface will look like. It is pretty thick. And the friction here, mu is equal to 0.5. Now what you did, we choose this as x-axis and we choose this as y-axis. You have taken a coin and you projected perpendicular to the motion of this with 4 meters per second. So coin enters perpendicular to the motion of this conveyor belt. The velocity of the belt. So the coin is coming from outside and then it enters inside with 4 meters per second. But the belt itself is going with 3 meters per second. And you're entering a rough surface. The first question, find the minimum width of the belt so that the coin does not come from the other side. I don't want the coin to go and fall out from the other side. Find the minimum width so that the coin does not cross the belt. It should not go to the other side. The second part, if the coin does not cross the belt, find the minimum speed of the coin. Okay, let's get this thing. This is a good one. Mm, 2 meters. Yeah, that is right. Find the minimum speed. 1.6. No. See, first thing. What does friction do? Remember, friction opposes relative motion. So that word itself tells you something. So if I can stop the belt, it'll be relative motion, right? So friction opposes relative velocity, right, Rohit? So let's solve the problem with respect to the belt. Because if you try to see this on the ground frame, it's really little confusing. Like, how is the relative velocity? Friction does not oppose your velocity. So be careful with that. Friction is not in the y direction. Friction opposes the relative velocity. Since the velocity of the belt is constant, there is no pseudo force. So that is one good thing. If the belt is accelerating, then you should take the acceleration pseudo force also. A belt is zero, so there's no pseudo force. So now if you stop the belt, this is how it feels like. So this coin will think I'm going up with 4 meters per second. I'm also going left side with 3 meters per second. So this is what a person who is standing on the belt will think. So he will think you're going in this direction with 5 meters per second. That's your initial velocity. This is the path of the coin. That's what the person on the belt will think. In the ground frame, it might be a curve or something. And this angle will be tan theta 4 by 3. This angle is 53 degrees. And the friction will be also backward. So this will be your F max, which is mu mg. This will give an acceleration in this direction, which is mu g. Mu is 0.5. So this is 5 meter per second square. So if you look at the coin ka perspective, the coin will think I'm going in this direction with 5 meter per second. And I have a deceleration A is equal to 5 meter per second square. So this coin will go in this line here and somewhere it will stop. We can use v square minus u square is 2s. So that will be your final velocity is 0. This is 5 square. This is 2 minus 5 and s. We get s is equal to 2.5 meters. But be careful, this is the slanting length. So on this, you want the coin not to fall on the other side. So we are assuming you just reach the corner and stop. So this is where the coin comes and stops. And this length was 2.5 meters. And this angle was 53 degrees. So this was the width W. So sine 53 is W by 2.5. And sine 53 is nothing but 4 by 5. That gives you 4 is equal to 2 meters. Check. So if you stop the belt, suddenly the question becomes easy to see. Is the thing clear, everyone? See, because friction opposes relative velocity. So stop the belt, you get relative velocity. So whatever the belt thinks the velocity, friction should be opposite to it. Any doubts on this part? The second part, get the minimum speed. That's actually the better one. If this is a paragraph, the second is a tougher one. Let's see how will you find the minimum speed. If they don't mention anything, it is always in the ground frame. Huh? Be careful with that. This is the path of the coin as seen by the belt. It's not actually going in a line. What is the minimum speed of the coin? Any answers? How do we do that? See, so this guy on the belt, he will think it is going this way with this acceleration. So at any instant, your velocity, which is v, right, that would be how much? So you are going with a speed of 5 meters per second. So this is velocity will be u minus at, so 5 minus 5t. Now be careful, what is this? This is the velocity of the coin with respect to the belt. Now you want in the ground frame. So velocity of the coin in the ground frame is velocity of the coin in the belt ka frame plus velocity of the belt in the ground ka frame. You just have to add them vectorially. Now here, if you are do it mathematically a little smart, your life actually becomes easy, or else it does get a little complicated. So just let's try to add the velocities on the coin. You will see what you are getting. So the belt is going horizontally, which is 3 meters per second. This coin is going at an angle here, which is 5 minus 5t at an angle of 53 degrees. So I have to add these two vectors and vectorially, and then I have to minimize this function. Now here, one way to do this, assume this is your x-axis and this is your y-axis. I'll show you why. I'll take a general one also and you'll understand. So if this was 53, this was 53. Now resolve the components. So I'll choose this as y and this is x. Now, if you look at the velocities, we have 3 sine 53. This will be 5 minus 5t. And this will be 3 cos 53. So the net speed, anyway, you just want the magnitude. So speed of the coin with respect to ground will be the resultant of these vectors, which will be root over 5 minus, how much is 3 sine 53? Cos 53 is 4 by 5? 3 by 5. So this is 9 by 5. This is 12 by 5. So this will be 5 minus 5t plus minus 9 by 5 ka whole square plus 12 by 5 ka whole square. Look at this function. Huh? We need to minimize this, okay? And this thing has two components. This guy is changing with time. So this whole component variable with time. And this guy is constant. Now you tell me how to make this value minimum. For minimum speed, this has to become 0, right? Because you can't change this value. The only value you can change is the left-hand term. So for minimum speed, this term will become 0. For minimum speed, this term will be 0. That means the minimum speed of the coin will be 12 by 5, which is 2.4 meters per second. Is that making sense? I divided this in such a way. See, there is only one vector which is variable, 5 minus 5t. So don't mess with it. Keep it as it is. Divide 3 into components. Now you have created a vector where there is one component is changing with time and one component is constant. To get minimum speed, the one who is changing with time will has to become 0. Is that making sense? Now, but if you say like, no, I won't take like this, then what would happen? Nothing wrong. You will still get it. It'll just get a little lengthy. This will be 3. This will be 5 minus 5t. Because sometimes, yeah, you don't get an idea there. Now, if I try to do this regularly, now if you try to write the speed, see how you get the equation. This will be root over 5 minus 5t. That would be sine 53, which is 4 by 5. Ka square plus 3 minus 5 minus 5t cos 53 ka square. Now, did you see the problem there? Both are variable with time. This is variable. This is also variable with time. Now we have to use maximum minimum. And then we have to do now dv by dt is equal to 0. You'll get the answer. You're getting the catch? So what happened here is the one who is messing up the whole thing is this guy with time. And now what you did, the one who is messing up, you made it into two pieces. Now both are messing up. A better way would be this. The one who is changing with time, don't mess with him. The other one who is constant, split him. Then we can say the variable component has to become 0 and the constant, you can't go below this. So the minimum answer is 12 by 5. Are you clear with this? So this is not a concept as such, but mathematically, if you're a little smart, it will save you some time. Any doubts on this? And did you observe here, the speed is actually less than 3 meters per second. It is lesser than the speed of the belt. Any doubts on this? Clear? Manav, Karthik, Anish, Dhruv, cams on everyone. Keep your cams on. Let's see one last one. This is a decent question from Eredo. Yeah, this question, right? Meaning there is a way to do. If you know, you know, or else you don't know. That's the problem. You need to know the process. So let's give it a try. Read the question, then I'll give you the picture. I'll explain it again, and then we can try. There are certain questions like that, where kind of you are remembering stuff. You're remembering how it is to be done, or else there is no way you will get an idea in the exam. You will run out of time. What is he saying the question? See, I'll try to draw the picture. So we have an incline like this. Able to visualize how it is? It is just a wedge where this angle is alpha. Right? Here we have the coin here. You projected it this way with a velocity v naught, some velocity. And these are the forces there. Now, when you projected this guy, the one who is dragging you down is your mg ka component. This will be mg sine alpha. That is the force which is dragging you down. Initially, this angle was 90. You're projecting it at a 90 degrees. And now what will happen? The horizontal velocity, there is a friction also here. It's not even smooth. It is also rough. So this guy will actually start going in some weird path. And at some point, your velocity has become v. At this instant, you're making an angle phi. And this phi is a variable. Every moment, the phi is changing. I hope the picture is making sense. The same thing, if you look at from the side view, it looks like this. This is the coin. You will see this is that mg sine alpha, which is dragging you down. This is this mg cos alpha, which gets balanced by normal reaction. So mg cos alpha is useless. And how is the frictional force? Remember, frictional force will be always opposite to the velocity. So for this, the particle F bar will be in this direction. And that will be maximum because you're sliding. The friction is opposite to V bar. I hope the picture is clear. So we have a wedge which is rough and you have thrown it parallel to the surface, but perpendicular to mg sine alpha. And now he's asking, find the velocity as a function of phi. So yeah, let's try to find V. So find the velocity when the angle is phi. He gave you that phi becomes 90 degrees, meaning eventually this thing will become like this, means it will become parallel to mg sine alpha. So, but let's try to find the velocity as function of phi. But is the picture clear, everyone? So you can just take your book, if you have your book, right? If you just keep it like this, isn't that how it looks, kind of? Uh, it's like this. If this was the incline, can you see this? So this was the incline, and this was the coin kind of thing. So if you look at this front view, right, it is going like this. So the side view will look like this. This, whatever is the coin here, is sliding here and coming down. Able to visualize that? The picture is clear. Think for a minute. Let's try to get the equation, then I'll show you. So there are totally how many forces on this? There's an mg sine alpha. I'll write this also. There is an mg sine alpha, which is dragging you down. There is a friction, which is opposite to your velocity. Yeah, and that angle phi is also changing. Everything is messed up. Yeah, this is the question. So how do we write this? See. So let's divide this into two parts, okay? For convenience, let's call this guy as your y-axis, this as your x-axis. We are taking x and y along the incline. So first thing, let's write the equations along y-axis. So there are only two forces there, F max and mg sine alpha. So in the y-axis, what are the forces? Mg sine alpha, which is along the y-axis, and F max, this angle also will be phi. So F max cos phi is equal to mass into acceleration in the y direction. Since it is slipping, the friction is equal to minus mu mg cos alpha, cos phi. is m into ay. But it is given in the question, the coefficient of friction mu is equal to tan alpha. That's what actually makes this question solvable. So mu is equal to tan alpha. So when you substitute there, suddenly that mu mg cos alpha becomes mg sin alpha. Because mu is tan alpha, cos will cancel. M gets cancelled everywhere, and you get ay is equal to g sin alpha, which is a constant. Alpha is constant, and 1 minus cos phi. Phi is a variable, and so this ay is the component of acceleration in y direction. This is not the net acceleration. This is only in y direction. This is the component of acceleration along y direction. So that's your equation 1. Clear with this? We just wrote the forces there. Now, same thing. This time, let's write the equation along the velocity. Equation along v bar. Meaning you are choosing to write forces along in this direction, along the friction. I scribbled a lot there, so let me just redraw it again. This is your F max, and this is your mg sin alpha. This was phi, and this was your velocity v bar. So if you write equations along the velocity v bar, so friction is anti-parallel. So we get mg sin alpha cos phi. So mg ka component minus friction F max is equal to m into a. So, and this would be your acceleration along the velocity. This a bar is along v bar. And then again, F max will be mg sin alpha cos phi. This will become again minus mu mg cos alpha is ma. This will become mg sin alpha cos phi. This again becomes mg sin alpha. This becomes m into a. So this is the acceleration along the velocity. So we get a is equal to g sin alpha into cos phi minus 1. And this is nothing but dv by dt, the rate of change of speed. Acceleration along this thing. So now there we got two equations there. See, we got ay is g sin alpha into 1 minus cos phi, where phi is a variable. I don't know how much is that. Acceleration along the velocity, this is also called as tangential acceleration. G sin alpha, which is cos phi minus 1. The only reason it is working is because mu is equal to tan alpha, or else that mg sin alpha won't come out common. Now, when you equate them, you will clearly see ay is equal to minus a. Ay will give you velocity in the vertical direction, whereas a will give you net speed dv by dt. And this would be simply dvy is equal to minus dv. And when you integrate the limits, initially, what was the speed? Initially, you're projecting with v naught. Initially, what was the vertical velocity? Which was 0. So initially, this was your vx, and initially, your vy was 0. So the limits will be from v naught to v, and this guy ka limits will be 0, and the vertical component will be v cos phi. So this will give you v cos phi is equal to minus v naught. Bring it that side, and then you'll end up with v is equal to v naught by 1 plus cos phi. This is the speed as function of phi. And you said eventually phi becomes 0. Again, if you look at that path there, This was phi. This was your component Vy, which is V cos phi. That's your velocity at some point here. And initially your Vy was 0. Initially your Vx was V0. That was your total speed. And eventually you are going to become parallel to the surface. So when it becomes parallel to the surface here, phi becomes 0. He's asking what is this velocity? So this is the V final. V naught by 1 plus 1, V naught by 2. That's your final speed. So eventually it will go with this speed and friction becomes equal to mg sine alpha, 0 acceleration. Like I said, the only reason it worked is because mu became tan alpha. You got an mg sine alpha, which came out common. So this is basically rate of change of speed. This is not the net acceleration. If you take acceleration in the direction of velocity, what you're getting is the rate of change of speed. We also call it tangential acceleration. So what you're integrated here is the vertical component and the speed. It's a little weird. Definitely go through the steps. Like I said, right? If you have seen this question before and you know the steps, if it comes in the exam, you'll be able to do. But if you see for the first time, it's very difficult that you will figure out what to do. Yeah, but that's how you handle this. So make sure to go through this. We did almost 16 questions. Next class, we will do a very important thing called 2 blocks and 3 block problems. That's one important part. But I think mostly next class, we will wrap up the chapter. And then after that, next week, we'll start off with circular motion. So if you see the chapter, right, is mostly NLM. The only thing was to somehow figure out the friction cut direction and magnitude. Okay, that will wrap up for the day. And do remember there's a test online on Friday. So make sure to give. And any doubts, anything else, please stay back and ask, or else you're free to be. I'll see you guys again next Monday, same time. So take care, stay safe.